Hello, Gordon.
Hello.
Hello, guys.
Hello.
Hey, Darshan.
Hey. So there is a request I have from at least one of you guys. You'll have to volunteer. That is regarding evaluation. So we have to do this evaluation. I think some of you who have spent some years here before COVID, it used to be that you will give this in the classroom and I leave and you collect it and leave it to the leave it at the office, physics office. So we need to do the same thing. There is no one in the class. And so the request is that you will have to come and collect this from me, then scan one of the sheets, send it to all of you guys, all the students in the class, then get it back as email and submit it to the physics office. It's a reasonable amount of work, but I think I don't see a better option than that.
I think the school gives out like course evaluations that you can do online.
That's correct. I'm aware of that, but this is a departmental evaluation. So this is a separate one from the CT, Center for Technological Excellence, I think. Yeah. So you will probably get an additional one from there also. I think last spring, I remember this was done online. Just CT was only one, but this one, the department has requested me to do this. So, yeah. Is there any volunteer I can think of?
I could be on campus a little bit later today, so I can come by and get them if you'll be in Neckers for a little while after class.
Okay, sure. I'll be at the office and then, yeah, then from that point on how you do it, I don't mind. It has to come back to the physics office, right? Even if it is an email, once you get everything, I think if Yeah, I'm not sure how you collect it together. So maybe you'll have to print it again and put it in the envelope and give it back to the physics office. Is that okay?
Yeah, so can I just scan the forms and email them to everybody? They can print them, fill them out, and then scan it and email back, and then I can print them and bring them in.
Yes, exactly. Yeah.
Okay.
So what in the first trip you have to scan only one, I guess, because it'll be the same copy. You just send it to everyone.
Right.
And when it comes back, you print it, put it in the same envelope and give it to the physics office.
Okay. Yeah, I can do that.
Okay. Thank you very much, Christian. Yeah, that helps a lot.
Yeah, no worries.
Okay, so this last week of classes, and we have the final exam for this close exactly 1 week from today. So it's on Monday, and there is a homework due meanwhile on Wednesday. We talked about radiation, and in particular, we talked about radiation per unit solid angle, how much radiation is going into a particular solid angle from the charges that could be oscillating, or we said that if you have a current distribution, that acts like a source of radiation, and how much of the signal, like if you were to make an antenna, how much of the signal goes into a particular direction. Often, what is of interest is also what is the frequency distribution of the radiation, and we want to talk about that a little, and we will have to go back all the steps, and wherever there is a time, we will try to write the Fourier transform of that. Right? So earlier we talked about what is the angular distribution, and now we say ask in each angle if there was a time dependent source which is having more Fourier modes than just single Fourier mode. Remember, Fourier mode is the frequency dependence. Then what is the frequency dependence per unit solid angle? So this is broadly called the spectral distribution. Of radiation. And let's go all the way back. Remember that, or let me begin by saying what is the Fourier transformation, right? So if you have a function f, which is an arbitrary function f, which is a function of time, and you say its Fourier transform is a frequency dependent quantity, and that's defined as f tilde, a new function, which is a function of frequency. And you go from. It's pretty much like when you have a music, you can build music out of fundamental tones, and this will be your tones, and that's your basis vector or basis function, if you want. It's called Fourier basis here. Like sine and cosines are the are the basis functions for the Fourier modes. And this is how much of each of the tone, right? Like if you have 7 tones you are breaking up into in music, then how much of each tone is necessary to construct a certain musical element. If you want the opposite, which is called a Fourier inverse, we will say tilde of omega is t. Notice 2 pi is not distributed equally there. And the only big major change is the plus I omega t instead of minus. So the idea is that if you know the signal, which is a time-dependent signal, then there is a unique set of frequencies that is used to construct the signal. And if you know the signal, then if you know the Fourier part of the signal, Fourier modes that construct the signal, then you know the signal itself. So either you talk about the signal or its components, right, or its modes, as we say. It's like saying if you have a vector Hello? Can you guys hear me now? Okay.
Yeah,
Hello?
I can hear you.
Yeah. Sorry about that. So I think this has happened a few times before. And by the way, it is only in this class this happens. It is most probably this almost never happened in other class, if not at least maybe once or something. So weird. Yeah. So I had to reboot the computer and come back. Okay. So were you there when I went through the, I didn't realize when you guys were disconnected. So did you almost see the whole expressions that I was writing on the
Yes.
board?
You had just written the transform from the second transform, and you were comparing it to the components of a vector.
Okay. So yeah, so let me mention that. So it's almost sort of a review. So you have if you have a time, this is the Fourier transform, which is a frequency dependent quantity. If you have the frequency dependent quantity, you can talk about the time itself. I had a tilde earlier and I deleted, I dropped that, saying that I will use the same function, functional form to represent the both, but that doesn't mean that it's the same function. Dependent argument will decide what function it is. So in principle, it is not, but just for simplicity, I'll do that, or not simplicity, for being laziness, I would say. I'll do that. You, in general, a field is a function of position and time, and you can do the same thing for position also. So there are three positions, so there will be three wavelengths if you want, and this will be called wave number. So it is 2 pi over lambda, exactly like frequency. This is 2 pi times frequency, and wavelength, it is 2 pi over the wavelength that you say is the wave number. Since there are three of them, so you provide three of the 2 pi's there, and this is e raised to minus I omega t. And now you have to provide three exponentials there for each of the lengths, and you write that as a dot product. So this is the same as kx in the x direction plus ky in the y direction plus kz in the z direction. So that's your three Fourier components conveniently written as a vector. And notice the sign change, that is because of the spectral. In special relativity, we realize that, oh, it's a good construction to have when the position has a positive and the time has a negative sign. So that's the motivation. It doesn't matter even if you were to write it as negative, that's just a notation in that sense. And the Fourier mode is written as k this time and omega. Right? All the positions get replaced by k's and all the times by omega. And again, remember, this is not the same function. We mean to say this is f tilde. So that should be f tilde, but we get lazy and we don't differentiate between the two. And it will be understood that whenever the argument is in the Fourier space, that's a different function, even though we write the same function to represent it. Okay. So that's a reminder of your Fourier transform, and let me write the inverse Fourier transform also. So that's k omega is equal to d cube or dt, d cube, or and change your exponential sign of the exponential. This becomes I omega t e raised to minus I k dot r, and here it is f of r t. So with this information, it is sort of straightforward in a sense. We have the expressions for the electric and magnetic field for radiation as a function of position and time, just Fourier transform, and we can get this. But it is nicer to go all the way back and get it at each level, because remember that we averaged over time somewhere in between. So we lost some information about the time dependence there. So let's go back. It is instructive to see what happens. So we go back to the very first expression for the electric potential. So for the electric potential, we had as a function of position and time, we had 1 over 4 pi epsilon naught. And integrate over both the sources and the time at which all the sources were radiating. And we had delta function, which is evaluated at t minus t prime minus r prime over c divided by and the source itself. In statics, we would have integrated only on the source position of the sources. Here we integrate on the time also, and that's minus infinity to plus infinity. T is the observation point, and T prime it is other points in the past wherever the sources were emitted, and R prime is the positions at which these charges were set. So you scan for the whole sources. Right at this stage, let's do the Fourier transform, and we just have to integrate it, right? We just now wrote down the Fourier transform so we can get the frequency dependent quantities. And before that, let me remind that the vector potential also has exactly the same form. We did this sufficient number of times. It's good to remind ourselves instead of just pointing into that. That's dt prime, dq r prime. Everything is the same, except now it is the current that contributes to the vector, but the magnetic vector potential gets contribution from the current density instead of the charge density. Idea is that we want to do the Fourier transform of this quantity. So we would say only the time at this point. We'll come back and talk about how we can get the position also Fourier transform. It will come automatically in a sense. So the frequency dependent piece of the electric potential will be get this whole expression at the very fundamental level, even before specifying the configuration. We just have to integrate over all time, all observation times. We already are integrating over all the emission times, but now we, in a sense, average out all the time components and we get frequency dependent. Oh, actually, I don't want to write the whole thing. I actually want to clarify that this is e raised to I omega t plus and phi of r t. Right, so I want to substitute this whole piece in here and do the integral, and we will be able to do this at a very formal level and get a lot of simplification right at this stage itself. So that's what I was doing in the next step. So let me write that again. So phi r omega, the frequency dependent electric potential is equal to time dependent, that is T prime dependent, and that is dq r prime. That is exponential of I omega t, the delta function t minus t prime c and charge. Oops, there should be a 4 pi epsilon somewhere, so I'll write that 4 pi epsilon here. notice the delta function allows us to do an integral, and I will use it to do the t integral. Earlier we were doing the t prime integral, so we will use the Fourier transform, or sorry, the delta function to do the t integral. So what it will do is that wherever there is a t, it will replace it with t prime plus r minus r prime over c. Right? That's what delta function does. It's decided by the argument of the delta function. And where is t sitting in outside the delta function? That's in the exponential. So I replace the t in that exponential with this, and that's the way you will do the t integral gone. And what will be left with will be a t prime and d cube r prime. And this time we have a frequency dependent quantity. So that's exponential of I omega, and this is t prime plus r minus r prime over c divided by r minus r prime and t prime. But there is a nice feature in this. So notice the whole time dependence can be separated out, or the time integral, I mean, the time dependence in the inside of the integrals can be separated out, and there is an observation there. That is, let me separate this out. So that's I omega over c divided by r minus r prime, and you have a time integral and if you compare the time integral that I've written now with one of those first few expressions I wrote for the Fourier transform where I was defining them, it turns out that this is actually the Fourier transform of the charge density itself. So this is equal to equal to 1 over 4 pi epsilon naught d cube r prime. And I have exponential I omega over c times r minus r prime over r minus r prime times the Fourier transform now only in the time space. So now it is in the frequency. So the idea is that instead of, if you want the scalar potential in the frequency domain, first convert the charge density into the frequency domain. Remember, now we are doing time dependence. And change your Green's function. Earlier we had a Green's function only on 1 over r potential, but now there is an exponential dependence in there. And each frequency has a different exponential component in that. And let's try to see that in a little more detail. If we were to think of, for example, omega is equal to 0, this is not that at all. The exponential transformation of the Green's function is not there at all. It goes all the way to infinity, but otherwise there is an oscillatory combination or contribution coming in from that. So that's good, but can we do more than this? Yes, we can do more than this, because as of now, we have not yet used the radiation approximation. So at this stage, let's do the radiation approximation. Remember, or the far field approximation, I should say. So this is r minus r prime is approximately r minus r hat dotted with r prime. that's your approximation, and in the denominator we understood that you need to only keep the first term. The exponential you keep both the terms, and the denominator you only keep the first term, and that's the leading contribution. In fact, at least in the electric potential, that's your leading contribution. So our electric potential is 4 pi epsilon naught, 1 over r comes out, right? Because this I replace it with the first term, that's 1 over r, and whatever is remaining is d cubed r prime exponential of I. Let me rewrite omega over c times r hat. Wherever I see this quantity, I will call this k. Okay. So this will be, first let me maybe explicitly write this. So this is vector r minus r hat dotted with r prime. So what that means is I can take the r out, r dependence, I'm doing the integral in r prime, so r dependence can come out of that. And it is what it is. I'm going to define this quantity here as vector k. That means omega over c is simply the magnitude of this quantity, which will be the magnitude of vector k, which is k itself. So this, when it comes out, can be written as exponential of I k r over r. The whole quantity comes out neatly written. K, remember again, is omega over c. I will specify this better. So k is omega over c, and vector k is omega over c in the direction of the observation from the source, that's r hat. So this takes the form d cube r prime, and this is minus I, again omega over c times r hat, that's nothing but k, vector k times r prime times again, if you compare with the first few expressions we wrote down in the class today, this is again a Fourier transform of the charge density. Already we Fourier transformed the time to get into the frequency domain. Now we are if we Fourier transform this position dependence using this expression, we reach the wavelength, wave number space. And the electric potential has a completely closed form, and it is rho of k and omega. That's it. So if you want to get radiation, it seems it is significantly simpler in the Fourier transformed space, in the sense all the r dependence completely comes into this exponential and r. Remember again, radiation is determined by 1 over r dependence in the electric and magnetic field, not in the electric potential. So that's your r dependence, that's your r dependence. Notice this does not have any r dependence. And the frequency dependence is completely now intertwined in the time place also, and in the position. When you transform the position into the wave number, there is some piece that goes into that also. If I were to repeat this for the magnetic vector potential, it is understood that it will be exactly the same thing will go in there also. And what we'll get is A of R omega would be equal to, except there it will be the current density in there, right? So this will be mu naught over 4 pi times exponential of IKR over R times now the Fourier transform of the vector potential. Right, that's your two pieces. And if you want the spectral distribution of the electric potential and the vector potential. If you want to get the spectral distribution of the electric and magnetic field, now we need to take the derivatives of this quantity, right? And then do the Fourier transform again. So let's see what that is in the last 10 minutes. I think I should be able to do it.
Dr. Shardesh.
Yes, please.
Wait, is the vector potential dependent on the current density?
Oh, sorry. Yeah, that's the current density, right? Yeah. Otherwise, it's meaningless. Yeah. I meant that. Yeah, sorry about that. That's it. Yeah, that's clear, right? Yeah. Sorry. Yeah, everything goes through because all the integrals, everything is the same. It's a vector. But thank you for pointing out. Yeah. Okay, so let's do the electric field now. So we have so remember, let's begin with a magnetic field, right? So we have magnetic field is magnetic field in the time and space. This will be del cross of A or T. If I take the Fourier transform on one side, it will be the same on the other side, but it's very clean here because if I'm doing only the time Fourier transformation, the gradient doesn't touch that at all, right? So the magnetic field in the Fourier space will be equal to the curl of the vector potential in the Fourier space. This curl doesn't get affected because everything is happening in the time domain, so it doesn't get affected. But we already know what the vector potential in the frequency domain is, so let's substitute that. It's mu naught over 4 pi times exponential of IKR over R, and we have our current density. And this is K, comma, omega. Remember again, K is omega itself, but it has a directional dependence in there. That's just a short form. If I want to take the curl of this, I have to hit it wherever there is an R. So there's an R here. It will hit this R, or it can hit the R in the denominator. And both are okay. But remember that radiation is determined by 1 over R potential. So this will be a 1 over R square potential. That will be a higher order. We dropped that even in the radiation potential that we were doing earlier. So we will not worry about this dependence, and we will worry only about that. So let's see what happens when gradient operates on. Do that here. Put it back. So whenever gradient, So whenever gradient acts on exponential of IKR, I get back my exponential itself, and it operates on whatever is in the argument of the exponential. Ik is a constant, that's Ik times the gradient of R is nothing but r hat. But k times r hat, k is the magnitude of, or magnitude of k is omega over c, right? That's times r hat is the vector k itself. That would be ik times exponential ikr. Right, that's what it is. So basically, what is happening is that gradient is getting replaced with I times k. So overall, in the radiation zone, this is equivalent to getting replace all your gradients with I times k, vector k, and you get your radiation radiation formula. We are actually dropping this 1 over r dependence in there, but that's okay. That's okay in radiation. So what we get is basically I times k crossed. Let me put that inside in there. So you have mu naught over 4 pi times exponential ikr over r times I times k crossed with j k omega. So we have the magnetic field expression at this point. Remember when we were writing the magnetic field expression in the time domain and the angular distribution, when we were interested in the angular distribution, we wrote it as r hat times that quantity. So let me again invoke k is omega over c times r hat, and let me take the c on the other side. I can write d omega. So that's a spectral distribution of the magnetic field, but eventually we are interested in the power radius. So that's c times magnetic field. So I write this as mu naught. Oh, sorry, r hat. I want to move it out. So that's r hat crossed with mu naught over 4 pi times there is a 1 over r, and there is an I omega exponential ikr times I omega over c. I multiply and divide by a c crossed with j, right? So this j. If you compare this with your radiation field in the time domain, you will see that it's pretty much the time derivative got replaced with I omega here. Otherwise, most of the terms would look pretty much the same. Okay, so that's magnetic field, but now we can talk about the electric field also. So electric field, similarly, is negative gradient of the scalar potential minus the time derivative of the vector potential. Did I miss a sign? Just checking on this. Yeah. Okay. Actually, when we wrote the magnetic field expression, we wrote it as the negatives of a curve. Let me introduce the negative sign in there. And it is good to introduce the negative sign in this minus I omega. So let me write that as minus I omega over c. So that's the replacement we will use for the swapping time derivative with this minus I omega. Okay. This quantity goes pretty much the same as the magnetic field. It is the same gradient. Electric potential has exactly the same form or pretty much the same form as the vector potential. So we will have very similar expression, except that instead of the vector or the current density, we will have the charge density. And so we will get this will be equal to minus r hat like that. It's just r hat, not right. The minus r hat mu naught. There is no mu naught, so this time it will be 4 pi epsilon, right? So will be 4 pi epsilon naught, and that will be 1 over r exponential of I k r minus I omega. No c because I got rid of the c in there, and then there is rho k omega. I think that's what it will be. I should check the factor of c there. Hopefully I haven't missed it. Yeah, and actually there is a c there. So there is a c because I had to bring in the c out from the left side also. And it is better to write this as I omega c over r hat because it was the gradient. So I'll write this as I k hat. It's the best return this one. I just collected the r hat. Earlier we split this out. I just brought it back. I think it is, I'm using this expression. I think it is still on the board, yeah. I'm using this expression there. So IK, bring it back. And there. So there was a, instead of mu naught over 4 pi, there is a 1 over 4 pi epsilon naught. That's all that changes there. And now let's do the negative time derivative of the vector potential. The time derivative, one has to substitute it back in there. But remember that whenever I was doing a time derivative, the only thing that happens is that the time derivative gets replaced with minus I omega. So what we can do is, it's pretty much the same. It's minus mu naught over 4 pi, same as whatever your A is, exponential of I k r over r. I'm reading out from the board, and the time derivative gets replaced with minus I omega, right? That's what we did. Where was it? A k omega, and this it gets replaced with minus I omega times A. And that makes it a plus.
Could you move the camera down, please?
Oops. That's all. Okay. Right. How can we see this more explicitly? And it's time, but if you allow me to go about 5 minutes to less than 10 minutes, I think I should be able to finish this. So remember, we can go on to the other board. Remember, we have the current conservation equation, d rho over dt, or t plus gradient with j. If we Fourier transform this, we will have to move d by dt with minus I omega. Gradient gets replaced with I times vector k. That's the time change in the sign is because of the Lorentz factor that we have been using, and then switch all the R and T's. Right? So this will be minus I omega times rho of K omega plus I times K dotted with J in the Fourier space now. It's K times omega equal to 0. But we do this explicitly, but after a few steps, you realize that it is basically got the prescription is just this. You don't really have to go through these. But in principle, at least once you should go through this in detail. So what we have is I times omega times rho of K omega is equal to I times K dotted with J. So that frequency dependence and the charge density is related to the frequency dependence and the current density in this. If we go back now and use this feature to replace my one of the, so remember K again is omega over C times R hat. So wherever that I omega times rho is there, I want to replace that. And I again made the mistake here, right? This is J, so this should be J, right? Sorry again. So it's J. That's the third time. Okay. And it is visible. So this is equal to, there is an R hat in there, and there is a C. So I replace the I omega that's remaining in there. So R hat over C, R hat times 1 over 4 pi epsilon naught times C e raised to I k R over R, and whatever is remaining I omega rho hat is I k dotted with J, and the other piece in there is is plus mu naught over 4 pi times, and I want to write this as R hat, right? So this is let me just finish this. It seems to be I'm missing something. I'm missing a sign there. I think so. Oh yeah. So if I go a few steps back, I wrote down this row pretty much by copying this. I said that, so this was B, right? So this was del crossed with A, which was equal to B. Is that visible to you guys? Yeah. Oops. Where am I writing? Yeah. So this quantity in here, so basically the gradient is getting replaced with I times K. So I said the gradient is getting replaced by I times K, but there's this negative sign in front which I have to take care of. So I should be putting in that negative inside. So that's a correction. So when I was doing pretty much by copying from the top, I forgot the negative sign. So please change that. So that negative sign comes in front here. That's the change in the sign. And let me rewrite this a little bit more. I want to write this K hat as I times omega times R hat. And there's a C which I will write down here. It's just rewriting. And did I, oops. Okay, so again, I changed that negative sign there, that went in here. That negative sign showed up here. This was written as a k hat earlier, k vector k, which I wrote as omega over c. One of the c's I wrote here, and there is the r hat. And rest everything stays the same. And that basically is so that I can identify this as 1 over mu naught. So that's a mu naught there. There's a mu naught ik over r, all that can come out. I e raised to ik r over r. And there is an I omega also. Whatever is remaining is minus r hat times r hat dotted with j, and the other term is basically r hat dotted with r hat, which is not here, but that's 1, right, times j, which from exactly the same thing happened in the time domain also. That's a cross product. This square bracketed term is r hat crossed with r hat crossed with j with the negative sign. Right? The first term gives you r hat in the direction of r hat, and the second term gives you the direction j hat. So this whole thing can be written as minus r hat crossed with r hat crossed with whatever r, and then there is I omega times j. Which is nothing but minus r hat crossed with c times b in the frequency term. So we get exactly the same expressions, except that the expression for the magnetic field has changed. So let me, in the last 1 minute, summarize what we have. We have in the frequency domain, we start with C times B magnetic field of omega. This is visible. Oops, not. Okay. That's equal to minus r hat crossed with mu naught c over 4 pi times 1 over r, and there has to be some form of current there. So this is e raised to I k r minus I omega over c times j. And the electric field is equal to minus r hat crossed with c times b or omega. And I think as a quiz, I will ask you to show that c times b from this. You don't really have to use those expressions. This is the same idea as before. This is actually just r hat crossed with electric field. So this serves as a quiz, the last. That's all. Thank you for allowing me to take extra time. And from this point, I think we'll come back and do some actual examples. Thank you.
Thank you. Dr. Shardish, how long are
Yes.
you going to be on campus today?
Tell that again.
How late will you be on campus?
Yes, I will be there. You should be here before 4, right? If I understand.
Yeah, I can get there before 4.
Yeah. If
Okay.
I should be there until then for sure. Even if you're a little late, that's okay. Right? I'll be there.
Okay, I'll be there.
Okay, thanks, Christian.
Yep.